Chapter 3.2 Part 2 Electrical Circuits Rules. This is where we will see the Kirchhoff's first law and the second law. Previously we saw them in the chapter, but the names were not mentioned, but we will see that here. Kirchhoff's first law is also called the Kirchhoff's current law, and it is the law which shows the law of conservation of charge being used. And the Kirchhoff's second law is also called the Kirchhoff's voltage law, which states that the sum of EMFs around a loop is equal to the sum of potential differences. Now, this is an example of the law of conservation of energy. And you can see the two laws are given here. In this book, you can see it's called the electric current rule. Without its name, they mention it. So, depending on the different books also, you can have these different names. Kirchhoff's first law, also called the Kirchhoff's current law. Some people pronounce the name as Kirchhoff. Okay, I think that is the most correct pronunciation. Kirchhoff's current law. Okay, so Kirchhoff's first law is Kirchhoff's current law, and it is also called electric current rule, which states that the algebraic sum of currents at a junction is equal to 0. So this is another way of saying the same thing, which says that the sum of currents entering a junction is equal to the sum of currents leaving that same junction. Also, we can say the algebraic sum of currents at any point is equal to 0, because the sum of currents entering should be equal to the sum of currents leaving. So if you consider the directions and add them together, it will be equal to 0. That's why we say algebraic sum. But remember, current is a scalar quantity. So if it's a vector, you should be able to do vector addition. But we can't do vector addition here. That's why it's a scalar quantity. So we say algebraic sum. Then voltage circuit rule, the Kirchhoff's voltage law, also called the Kirchhoff's or Kirchhoff's second law, it states that around a closed loop, the algebraic sum of EMFs is equal to the algebraic sum of potential differences. You can see the Greek letter sigma is used to indicate the sum of. So algebraic sum of EMFs is equal to the algebraic sum of potential differences around a closed loop. So when you go around a loop, I previously explained this in the previous video also, the sum of EMFs is equal to the sum of potential differences. So we will see it in some detail here. By the end of this section, you should be able to understand how the distribution of current in a circuit is a consequence of charge conservation. I already explained that earlier, so I will go through this a bit faster than what I did in the previous part 1 video of the same chapter 3.2. Understand how the distribution of potential differences in a circuit is a consequence of charge conservation. Many calculations based on current and voltage circuit rules. So we will do calculations with this. Now this is the person, that's why it's called the Kirchhoff's or Kirchhoff's laws. Okay, so see, and there are also laws named after him. And the electrical circuit rules presented here sometimes carry his name. Gustav Kirchhoff presented the conservation of charge and of electrical energy within a circuit as two laws of physics. So this is the first law or first rule, the electric current rule. The algebraic sum of currents entering a junction is equal to 0. Algebraic sum of currents at a junction or entering a junction is equal to 0. In order to conserve electric charge, the sum of all the currents arriving at any point, such as a junction in a circuit, is equal to the sum of currents leaving that point. So I already explained this. Now you can see it even here. 0.8 amperes come this way. So here is a junction or branch. It branches out here. There are two paths for the current to flow, this way and this way. So some of the current flows this way, some of the current flows this way. Now if they are identical lamps, meaning if they have the same resistance, then the current will divide equally. So 0.4 amperes goes this way, 0.4 amperes go this way. Now I1 is equal to I2 plus I3. Similarly over here, I2 plus I3 should be equal to I4. Now these two are in series, so whatever current that is going through this has to go through this. So this and this, the resistor, the ammeter and the cell are all in series. Therefore 0.8 amperes flows through them. And you can see it is done as a calculation here. The total current entering should be equal to the total current leaving, and you get it equal to 0. You can even do it by yourself. I already showed you. Now here if you add this and this, that is equal to this. So if you take just this point, let's say the point right here, now the total current entering that point is 0.8, total current leaving is 0.8. so if you bring all the terms to one side, it is 0. That's what we mean by the algebraic sum. That is the Kirchhoff's first law, and it is shown here also. So ampere is coulombs per second, so the total number of coulombs entering every second should be equal to the total number of coulombs of charge leaving. That's why we call it the law of conservation of charge. Being used here is showing as an example here. Then we have the Kirchhoff's second law, electric voltage rule. So around any loop, now here there is one loop, here there is another loop, even this, that, those are all loops as well. Even here you have a loop, but remember we don't consider the voltmeter actually, because it has a very high resistance. We assume no current flows through it, so no point taking it around the voltmeter in these cases here. Now let's try this one. Now here you can see this resistor is in parallel with this lamp. So you can see if you look at this loop here, now this diagram has too many arrows and all drawn here, too many symbols, but just take it as a simple diagram, just a resistor, a variable. This is the symbol for a variable resistor, and then a lamp. You can just forget about the voltmeters for now. So what you know is that around a loop, now we will consider this loop first, okay? The biggest loop that we have here, I think, is this one. So you know the potential difference across this is given. The potential difference across the cell is given, 3 volts. So the potential difference across this should be 3 minus 2.15, because the sum, now when you go around this loop, the sum of EMFs should be equal to the sum of potential differences, and this, they are in parallel. So even we don't need to consider this because we are just considering this loop. So you can verify it afterwards to be 0.85. Now let's first find what is the value of V3. We simply say that the potential difference across this plus the potential difference across this should be equal to this. You can even write it down, and you will see that therefore this minus this, so 3 minus 2.15 is 0.85. You can even you don't even need a calculator, okay? You don't need it, so 0.85. Now you know this and this, they are in parallel, so they will have the same potential difference across them, which is 0.85. So V3 reads 0.85, V4 reads 0.85 volts, and here these readings are already given. And you can see the calculation here, the sum of voltages. Here also you can take. Now here in this loop, there is no EMF. So it's only the potential differences, because this is a component that is using electricity. This is also a component that is using electricity. So the sum of EMFs around this loop is 0. That is the loop that contains the fixed resistor and the lamp. So around this it's 0. So that means here it should be 0.85. This way down also 0.85. So when you go around the loop, it's plus 0.85 minus 0.85, which will give you 0. So here you can see. Yeah, I think it's a mistake here. This should be V2 and V3, not V3 and V4. Because this and this, they are in parallel, so they will have the same potential difference across them. So it should be V2 and V3, not V3 and V4. Okay, so this is the Kirchhoff's second law, which states that the sum of EMFs around a loop is equal to the sum of potential differences. Now what is V? It is the voltage. I wrote it here earlier. So here you can see this example. Now if 1.5 joules, 1.5 volts is the potential difference of this, and then the potential difference of this will also be 1.5 volts, because you can see they are connected like this, they are in parallel, we can say. So the cell is supplying energy. to the electrons or the charged or the charges. So for every coulomb of charge, you know how much is 1 coulomb. So for every coulomb of charge, 1.5 joules of energy is given. So every coulomb of electrons, 1.5 joules of energy is given. It is converted to electrical energy and given to the electrons. So the battery or cell or power supply is like an electron pump. It pushes the electrons around the circuit. Now what happens over here is the electrical energy is converted to light energy and heat energy because because it is a lamp. When you have a lamp, it gives light energy and also it gets heated. So every coulomb of charge here loses 1.5 joules of energy. It gets converted to light and heat energy here. This is what happens when so eventually the battery dies because it's converting its chemical energy to electrical energy, and here the electrical energy is converted to thermal energy and light energy. Okay, then now okay, this is what I mentioned. So here it should be, yeah, here it is okay, V3 and V4. So V is equal to this is what I mentioned, 0.85 minus 0.85. That's why this should be V2 and V3, not V3 and V4. Then there are more calculations. Now you can see over here, voltage rule with calculated potential differences. So this is the Kirchhoff's second law. The sum of EMFs is equal to the sum of potential differences. Now instead of writing V, they write IR. Okay, now we can check this one. Now see here you have 1, 2, and this whole thing you can also take it to be a loop. This whole thing also is a loop. So then you omit this wire, okay? So in the third loop. So imagine this is the first loop, this is the second loop, and this whole thing here is the third loop. Even this is a loop, okay? So altogether you have even this whole thing we can count as one loop. But the best thing is we will see, okay? This and maybe even this whole thing. So we will see. Now the EMF, there is only one power supply here, which is this. So the EMF of this is and this will have an EMF of 4.5. Okay, so we can verify that even. Now here you can see how it is 4.5. We can check. Now if you go around this loop, let's say, so we will have, now we are not given V, so we will have to find V. So here the current is 0.45 amperes. So now if you consider this loop, the current is going like that. So here no potential difference because it's an ammeter. So the current here is the same as the current here and the current here. Now we can try. So we will use V equals IR for this first loop, which is at the very top. So I is 0.45. You can use your calculator right now. Actually you can even write it down, times 7.5. So that 0.45 times 7.5, we are using V equals IR. So I times R. The potential difference across this is 0.45 times 7.5, which is 3.375. Same way you can do it for this. So plus again 0.45. Remember this and this, they are in series, the same current flows through them. So I is 0.45 again, but R is 2.5. So we get 4.5. So you see, when you add the potential difference across this plus this, it will be 4.5, which will be the same as the EMF here. Now you can, so we got 4.5. okay, now we can do it using this loop also here. So this loop, but we need to know the current that is going this way. Okay, now again we don't need that current because this voltmeter is reading already 4.5 here. So you see, this cell here is in parallel with this resistor here. So if they are in parallel, they will have the same potential difference across them, and the voltmeter already gives the reading to be 4.5. So that means the EMF of this power supply, because it doesn't have internal resistance. Now again, don't worry about internal resistance. If you don't know what that is, later on you will learn that. Okay, so forget about it for now. So the EMF of this is equal to 4.5 because the potential difference across this is 4.5. So around this loop, if you look, here it's 4.5, the sum of EMFs should be equal to the sum of potential differences, and you have only one potential difference here, which is 4.5. So around this loop, that means the EMF here should be 4.5 because of Kirchhoff's first law, which states that the sum of potential differences around a closed loop is equal to the sum of EMFs. So total potential difference is 4.5. That means total EMF here, which is only this, should be 4.5, and we verified it going this way as well. Okay, now you can also do it for this big loop here, but if you consider the big loop, which is like, okay, going like that, like that, like that, then you have to omit this. So then you will see here it is, the current is going this way, but here the current is going the other way. So this way it is plus 4.5, this way it is, because its current here is flowing the other way, it's minus 4.5, so total is 0 if you consider the big loop here. Okay, because here no EMF, so that means the sum of potential differences around this third loop that I am showing right now here should be equal to 0, because there is no EMF around this path. So you know, across this and across this it's 4.5 plus 4.5, same direction as the current. This way it's the opposite direction, you can see the current is flowing, so minus 4.5, total is 0. Now the calculation is shown here. Okay, now this is actually for the first thing we did, the first loop, which is this loop right here. See, I told you can use the calculator. 0.45 plus times 7.5, I times R plus 0.45 times 2.5. okay, so that total is this, and that will be 4.5, which is equal to the EMF. Alright, so that's the end of that lesson. You can spend some time on this. I think you will get it when you do these examples, you will get better at it. Okay, so make sure you answer these questions, and that is the end of that lesson on Kirchhoff's laws. We had the Kirchhoff's current law, which is this one, and the Kirchhoff's voltage law, which is this one. Okay, next we will see chapter 3.2 part 3, potential dividers.